Welcome back everyone. In this lecture I will actually develop some tools called Casimir elements in order to prove complete reducibility of finite dimensional representations of semisimple algebras. So, we will recall with the Schur's lemma. So, I just recall some of the things that we have done in terms of representations. So, first we recall Schur's lemma. So, Schur's lemma states the following. So, if we have a representation, so let phi from G to GL of V. So, let us assume it is irreducible. So, then the only endomorphism of V, only endomorphism of V that commutes with commuting with all elements phi of x where x in G. So, they are all scalars. So, what is the meaning of this? Suppose if you have a map, let us say f from V to V such that, so this is a linear map. So, this is commutes with all this phi of x, x in G means it commutes with the action of G. So, that means it is actually a G module homomorphism. So, this is a G module homomorphism. So, then f must be scalar times sub identity. So, that is what Schur's lemma says if we assume V is irreducible representations of G. So, this is something we have already proved, I am not going to prove. So, I am just recalling this statement which will be used later. So, again we also define what is called this dual representation as well as this home of V comma W. So, let us quickly recall them. So, here is the definition of this dual representation. So, let V be a G module. So, then one can consider the dual space which we denoted by V star. So, which is nothing but all linear maps from V to C. So, which is denoted by home C V comma C. So, if we do not mention this C, it is assumed to be linear maps from V to C. So, this is called the dual space, and this dual space can be made into G module by defining the following. Okay. So, this becomes G module if we define the following action of G on this V star. So, how it is defined? So, given f in V star and x in G. So, the action x dot f, it is defined to be again a map from V to C. So, which is acting on some given element V in capital V as follows. So, this is given by minus f of x dot V, and this is true for all x in G and V in V and f in V star. So, this is something we have already checked. So, this defines representation G representation on this V star. Okay. So, given this G representation V, so we can actually use that to define G representation on V star. So, more generally one will be able to define on any home space V comma W. So, let us recall this home space. So, home representation. So, what it is? So, we start with two representation, let us say V and W. So, they are G modules. So, then we can consider this home space between them. So, these are all set of all linear maps from V to W. So, this is set of all C linear maps from V to W. So, now this home space can be made into G module by defining the rule x dot f which is acting on V to be just x dot f of V minus f of x dot V. So, this is for given x in G and f in home V comma W and V in capital V. So, this is something we already checked that this defines G action on this home V comma W, and this makes home V comma W as a G module. So, now we will see that. So, this is something I already left it as exercise. So, if you have not done this, you should definitely do it. So, if we have this G module home V comma W, so this is naturally isomorphic to the tensor product V star tensor W. So, this V star is already defined as a representation, G representation. If W is another G representation, then we can consider this tensor product of these two representation V star tensor W. So, that will be as a vector space naturally isomorphic to home V comma W. So, we say that that natural map is actually indeed G module isomorphism. So, this is as G modules. So, this is something one should definitely check. So, now we will define what is called this Casimir element of a given representation. So, this is actually a very important tool in order to prove complete reducibility for finite dimensional representations of semisimple algebra. So, let us define what this is. So, we start with G being semisimple Lie algebra, finite dimensional semisimple Lie algebra. So, using a killing form, we saw that many characterization of this finite dimensional semisimple Lie algebra, and we take actually a faithful representation of G, okay, which we denoted by pi. So, what is faithful representation? It is a representation of G. So, that is it is a Lie algebra homomorphism from G to GL of V, which is actually 1 to 1. So, this is a 1 to 1 map. So, that is faithful representation. So, this is the data we start with. So, then by imitating the killing form, one can define a bilinear form on G. Okay. So, that is defined as follows. So, define this beta, so which is actually depending upon this representation pi. So, which is a map from G cross G to complex numbers. So, this is given by beta of x comma y equal to the trace of pi of x composition pi of y. So, this is basically generalizes the notion of killing form to any representation. So, killing form, if you recall, it is kappa of x y given to be trace of add x composition add y. So, which is defined for the adjoint representation. Now, one can easily generalize that definition to any this representation pi. So, indeed we will see later that this being this 1 to 1 map is actually not that important. One can define this Casimir element for any given representation. So, we will come to that later. First, we will consider this particular case, and this is defined for each element x y in G. So, now it is immediate that one can easily check this beta must be symmetric bilinear form. Okay. So, beta is symmetric and bilinear form on G. So, this is something easy to check because the trace being linear and this product being bilinear. So, we get beta is bilinear and symmetric bilinear form. So, now because beta of x y is given in terms of the trace, now using the trace property one can easily check that beta is also associative. So, beta is associative. So, this is something I leave it to you to check. So, for what is the meaning of associativity? So, if we take beta and then compute this beta of bracket x y comma z, so this has to be equal to beta of x comma bracket y z. So, we have already seen application of this associativity when we are dealing with the killing form. So, one of the important application is that if we take the radical of this bilinear form, so that must be ideal inside your Lie algebra. So, what is the radical? So, radical is again defined very similar to for the killing form. So, this is those x in G such that, so this beta of x comma y is 0 for all y in G. So, this is called radical of beta. So, one can easily check this radical must be ideal inside G. Okay, this is something I leave it to you. So, this is very similar to what we have done for by killing form. So, now we can see that this radical is being ideal inside G. So, the elements of the radical satisfy this following property. So, if we take this trace of this pi of x comma pi of y, which is nothing but beta of x y. So, this is actually 0 for all x y inside this radical of beta. So, that means if we take the image of this radical beta, so which is actually inside your GL of V. So, this must be solvable. So, this is solvable Lie algebra using the Cartan's first criterion, because this satisfies this trace condition. So, that actually makes this pi of radical beta is solvable Lie algebra. So, now radicals being actually isomorphic to this pi of radical of beta, because pi is injective. So, radical of beta is actually isomorphic to pi of radical of beta. So, that implies this radical of beta is actually solvable ideal inside G. So, this is solvable ideal inside G. But since G is being semi-simple, so the maximal solvable ideal must be 0. So, that implies that this radical of beta must be 0. So, the radical of beta must be 0 as G being semi-simple. So, that means this beta, the bilinear form that we have considered, that is actually non-degenerate bilinear form. So, this implies beta is non-degenerate bilinear form. So, more or less all the properties of the killing form is actually carried to this beta. Okay. This is symmetric bilinear form and associative, and it is also non-degenerate bilinear form defined on this beta, defined on this G. So, this is something very important. So, now using this information, we will be able to define what is called this Casimir element. So, let us actually use this information. So, since this beta is actually non-degenerate on G, so given any basis, one can talk about a dual basis of that given basis. So, let us fix one basis. So, let us say that x1 etc. xm. So, this is a basis of G. Now, since beta is non-degenerate on G, so what one can do, one can actually identify a dual basis of this given basis x1 etc. xm. So, let this y1 etc. ym be the dual basis. So, be the dual basis of this x1 etc. xm. So, how the dual basis is defined? So, dual basis is defined with respect to the following equations. So, when we compute this beta of xi comma yj, so then we should be getting this delta ij. This is true for each ij from 1 to m. So, using this equation, the dual basis is actually uniquely determined. So, given xi, there exists unique yj's such that this beta of xi comma yj is equal to delta ij. So, if you have not seen this fact, you should definitely check this. So, this is an elementary fact from linear algebra. So, now we will use the associative of beta and then try to actually construct this Casmir element. So, which is actually element inside this endomorphism of V, which actually commutes with the action of G. Okay. So, what is the Casimir element? So, let me first define. So, the Casimir element of this representation pi is defined to be, so let us denote it by C pi of beta. So, a priori this is actually depending upon the bilinear form that we have defined. Of course, the bilinear form is also depending upon the representation that we have chosen. So, because of that we can suppress the notation to be C pi, there is no issue with that. So, how it is defined? This is actually you take all this pi of x I times this pi of y I for I range from 1 to m. So, this is an element inside your endomorphism of V. So, this element is called the Casimir element of this representation pi. So, what is the important fact? So, the fact is, which we will check now, this element that we have defined C pi, which is inside your endomorphism of V. So, this commutes with the action of G. So, this commutes with the action of G. So, what is the meaning of that? So, that means C pi commutes with pi of x for all x. So, that means the bracket between these two are 0 for all x in G. So, in particularly this C pi defines an endomorphism from V to V, which is a G module map. So, this is the consequence. So, the C pi is indeed defines an endomorphism of G module map. So, let us do this computation and then check this. So, for this purpose first we need to actually fix some notation and then see some relations between the coefficients that are involved in the computation. So, for that purpose let us start with some x in G and then you write this bracket x comma x I to be the summation a I j x j, where j runs over 1 to m. Similarly, we write x comma y I to be summation b I j y j, where j runs over 1 to m. So, now using the associativity, we will actually see some relations between the coefficients this a I j and this b I j. So, what is that? So, let us use this the associativity, using the associativity of beta. So, we get the following. So, what we get? So, we compute let us say a I k. So, which is given to be summation j range from 1 to m a I j beta of x j comma y k. So, this is just a definition of this dual basis. So, now what it is, if you just do the computation. So, this summation a I j can be actually taken inside. So, this is exactly equal to beta of summation a I j x j, j runs over and then comma y k. So, this is this element. Now, you can see that this element can be replaced by bracket x comma x I. So, this is exactly equal to beta of bracket x comma x I comma y k. So, now, so this can be rewritten as follows. So, using this skew symmetric among the Lie product, we write this as minus beta of x I comma x bracket with y k. So, now use the associativity and then rewrite this as minus beta of x I comma bracket x y k. So, now this bracket x y k is given by summation b k j. So, if you rewrite this, then we get minus summation j range from 1 to m b k j beta of x I comma y j. So, this is what we get. But note that beta of x I comma y j, it is a delta I j. So, in particularly, so when I equal to j, we get this coefficient b k I. So, this is exactly gives us minus b k I. So, this means what we proved that this a k I is nothing but equal to minus b k I using the associativity of beta, and this is true for all I k. Okay. So, now we will actually use this in order to compute the C pi with the pi of x, okay, the commutator. So, let us actually do that computation. So, for that computation initially we need one important identity. So, which is something very easy to check. I will leave it to you to check. So, this is the identity that I recall. So, if we take 3 elements x, y, z from this endomorphism of V and then if you compute the bracket x with y z, so then that should be equal to the bracket x y times z plus the bracket y times the bracket x z, and this is true for all x y z inside your endomorphism. Okay. So, this is some very easy computation. One can directly rewrite what is the meaning of this bracket a b, and then one can check left hand side is equal to right hand side. So, now using this identity, let us compute what happens if we take the commutator between pi of x and c pi. So, for any x in G, so let us compute this bracket pi of x with the c pi. So, this is by definition you can see that this is summation over I the bracket pi of x comma pi of x I times pi of y I. So, this exactly looks like the term the bracket x comma y z. So, we just replace this by what is there on the right side. So, then this is equal to summation over I bracket pi of x comma pi of x I bracket pi of y I plus again summation over I pi of x I times the bracket pi of x comma pi of y I. So, this is what we get. So, now you can see that the bracket x comma x I is nothing but given to be summation a I j x j, where j range from 1 to m. So, now if you apply pi on both sides, you can see that. So, this pi of bracket pi of x comma pi of x I is given by summation a I j pi of x j. So, now we will just substitute this inside inside this double star. So, then we get the bracket pi of x comma c pi is equal to summation the bracket I j a I j pi of x j times pi of y I. Similarly, on the right side also second term also can be replaced using this summation b I j. So, then this is summation b I j, where again I j varies pi of x I times pi of y j. So, this is what we get. So, now note that we already have this relation a k I is nothing but minus b k I. Okay. So, now using this relation you can see that. So, the terms that are involved here get cancelled. So, you get the bracket pi of x comma c pi is equal to 0. So, now using this we can easily conclude that the c pi actually commutes with all the elements of pi x, where x in G. So, that means the c pi defines G module map from V to V. Okay. So, this is very important observation. So, now what we are going to do, we are actually going to apply this when we actually take V to be irreducible representation and then see actually what is happening. So, let us actually recap what we have done so far. So, we started with the faithful representation. So, G being actually semi-simple Lie algebra, and we took this faithful representation from G to GL of V. So, now then using this representation we define this bilinear form beta from G cross G to C given by beta of x comma y to be equal to trace of pi of x composition pi of y for all x, y and g. So, then we observed that this beta is actually non-degenerate symmetric bilinear form. So, in particularly given a basis, we can talk about its a dual basis. So, we fixed a basis x 1 etcetera x m of G. So, then we took the dual basis. So, this is a given basis. So, the dual basis we denoted by y 1 etcetera y m of G. So, then we define what is called the C pi. So, which is summation pi of x I times pi of y I. So, which is an element of this endomorphism of V. So, now this element is actually commutes with all elements pi of x. So, that is what we proved for all x in G. In particularly the C pi actually defines G module homomorphism from V to V. So, now because of this definition of C pi, you can see that if we compute this trace of C pi, so that is something easy to compute, because the trace of C pi will be equal to summation trace of this pi of x I times pi of y I, okay, for I range from 1 to m. Now, note that this x I and y I, they are given to be dual basis. So, in particularly, so this is going to be your beta of x I comma y I. So, that is nothing but just 1. So, this is exactly going to give us m. So, which is the dimension of your Lie algebra. So, that means the trace of the C pi, which is independent of the basis that we have chosen. So, that is actually is indeed equal to the dimension of G. So, which is very important observation, because we know that if we restrict to this pi being irreducible representation, then using Schur's lemma, we see that the C pi must be some scalar multiple of identity. Okay. So, in case we take pi to be irreducible, so we are specializing to this irreducible case. So, then using Schur's lemma, what we see, this C pi, this must be scalar multiple. So, this must be some scalar multiple of identity on V. So, now we already calculated the trace of this C pi. The trace of C pi is nothing but the dimension of G. So, which is the trace of C pi, okay, which is also given to be now, because this is lambda times identity. So, this must be lambda times dimension of V. So, that tells this lambda. So, that we are actually looking forward to determine. So, that lambda is indeed actually given to be the quotient of this dimension G divided by dimension V. So, it is not just some complex number, it is actually a rational number, it is also positive rational number. Okay. So, this is actually positive rational number. So, that means the C pi, the Casimir element, it is not just only acting on this irreducible representation, it acts very explicitly by this rational number dimension G divided by dimension V. So, this is a very important observation. So, now let us see how one can modify this definition of Casimir element for any representation. So, when pi is no longer faithful, a slight modification is actually needed. So, that is not too much. So, what is the modification that we are going to do? So, now we just assume pi is general representation. Okay. So, there is no assumption on pi. So, you take pi to be representation of G. Again G you continue to be assume this is 5 dimensional semi-simple Lie algebra. Now, given this pi representation, so you can see that the kernel of pi, that must be ideal inside G. So, the kernel of pi, this is ideal inside G. So, we have seen that because G is semi-simple, G can be written as direct sum of these simple ideals. In particularly, any ideal inside G also can be written as direct sum of those some simple ideals from those simple ideals. So, what I mean by that? So, from using the killing form, we actually proved that G must be equal to G1 direct sum etcetera direct sum Gk, where these Gi's are all simple ideals inside G. So, they are simple ideals inside G. If we take any I which is an ideal inside G, so then we can see that this I must be equal to this direct sum of G I intersection I, where I range from 1 to k. So, now note that this G I intersection I, this is either 0 or full, because G I being a simple ideal. So, this is has to be either full or 0. So, that means you have a some subcollection of this G I such that this I can be written as direct sum of G I for some I in capital A, where this capital A is some subcollection of this 1 to k. And this is something we know already from the general theory. Okay. So, now because of that we can see that this kernel pi is also direct sum of simple ideals, some simple ideals that comes from G. So, now in particularly if I take G modulo the kernel phi, so this must be semisimple Lie algebra. So, this is again semisimple Lie algebra. So, in particularly this pi induces faithful representation of this G dash. Okay. So, let me call it G tilde. So, G tilde. So, this pi tilde, so this is a map from this G tilde to again GL of V. This is one can assume to be faithful, okay, faithful representation of G tilde. Note that, so now we have this pi tilde which is faithful representation. So, from our earlier arguments one can define what is called this Casimir element for this pi tilde. So, we simply take C pi to be equal to this C pi tilde. Okay. So, why this definition makes sense? Because this pi of G is same as pi tilde of this G tilde. So, that means what is the property of this C pi tilde? C pi tilde is an element of this endomorphism of V that commutes with the action of G tilde. But since pi tilde of G tilde is same as pi of G, so that tells us that this C pi tilde also commutes with the action of this G. So, that is the important property that we wanted, so that we get. So, note that, so this C pi which is C pi tilde commutes with pi of x for all x in G, because either pi of x is 0 if it comes from the kernel, or otherwise it is non-zero, in that case it just commutes. So, this is how we modify the definition of this Casimir element for general representations. So, we will actually use this information in order to actually prove the complete reducibilities of finite dimensional representation. So, for that I need one small fact which I will just recall now, and I will end with that result. So, what is that small fact that we needed? So, if we have this representation of the semisimple Lie algebra, so we can say something about the image of that G. Okay. So, let pi, which is a representation of this semisimple Lie algebra, be a representation of semisimple Lie algebra G. So, then what one can conclude immediately, the image of this G under this pi, that should sit inside SL of V. So, these are all traceless matrices, okay, or traceless operators on V. So, in particular if you restrict to one dimensional case, so if V is being one dimensional, then G must act trivially on this one dimensional representation. Why? Because SL of V is trivial for V one dimensional. So, in particular G acts trivially on any one dimensional representation of G. So, how one proves this? So, you can see that because G is being semi simple, so G is equal to the derived algebra GG. So, in particularly pi of g must be equal to the bracket pi of g comma pi of g. So, in particularly this should live inside SL of V, because so commutator of two maps should have traceless. So, that means if we take any linear combination of that, that we again will have traceless operators. So, now if we take V to be one dimensional, suppose V has one dimension. So, then it is immediate that this SL of V must be 0. So, that means pi of g must be 0. So, that means g acts trivially on this one dimensional space. Okay. So, since this g acts trivially on this one dimensional space, we already have this trivial action on this complex numbers, which is one dimensional. So, with the up to isomorphism we denote that by just a complex number C. Okay. So, this is what we denote it by one dimensional G representation of G one dimensional G representation. Okay. So, with this remark I will stop now. I will continue with complete reducibility in the next class. Thank you.